Imagine trying to teach an algorithm to predict the weather, but the underlying laws of physics change every Tuesday. That is the exact problem we face in time series forecasting if our baseline rules are constantly drifting. This split-screen visualization shows us the ideal scenario versus the reality we often encounter. A series drifts upward, expanding in volatility. Predictive models map historical patterns to future probabilities. Feed this bottom data into a forecasting algorithm, and it fails. The rules learned at the start of the timeline no longer apply at the end. Stationarity is the mathematical requirement for extracting historical patterns. Without it, you are asking your model to hit a moving target in the dark. The specific structural hurdle that ruins stationarity is a mathematical property known as a unit root. A time series with a unit root will continuously drift away from its starting point instead of reverting to a stable average. We can see exactly how this behaves when a sudden shock hits the system in these two side-by-side graphs. On the left, the stationary line spikes from the impact, but quickly curves back down to its original horizontal baseline. On the right, the unit root process spikes and stays there, forming a brand new baseline. If you calculate an average for this right-side graph, the calculation fails. The historical average is now entirely divorced from current reality. Every new shock to a unit root system overwrites the baseline. That constant overwrite ensures that any historical average you calculate becomes meaningless the moment the next shock arrives. You cannot rely on visual inspection alone to spot this drift. You need mathematical proof, and the standard tool for that is the Augmented Dickey-Fuller, or ADF, test. Here we have a snippet of Python code running the ADF test from the statsmodels library. The test operates on a specific null hypothesis, that a unit root is present. When we run this code, we get a p-value of 0.85. Because the default assumption is that the data is non-stationary, we need a p-value under 0.05 to reject it. Here, the test accepts the null hypothesis. A unit root is detected. Take a moment here. Based on a p-value of 0.85, what does this mean for your forecasting workflow, and what should you do next? Since the default assumption of the ADF test is that the data is non-stationary, a high p-value stops the modeling pipeline. You cannot forecast with this data in its current state. To fix this, we apply a mathematical transformation called first differencing. It strips away the trend and forces the data into a stationary state. First differencing subtracts the previous period's value, yt-1, from the current period's value, yt. We drop the absolute total, plotting only the remaining difference on a new flat axis below. Programmatically, calling series.diff followed by drop_NA generates this flat line. By discarding the absolute totals, you eliminate the drift. The model is now forced to learn strictly from the period-over-period rate of change. Before forecasting, you must verify the differencing actually eliminated the unit root. By running the ADF test a second time, Panel A's rising data fails the ADF test at 0.85. Panel B's difference data passes cleanly at 0.01. This establishes a three-step workflow. Check the plot, run the test, and apply differencing. Your model is now cleared to activate. Predictive algorithms require a stable mathematical environment to function. Before you can ask an algorithm to predict the future, you must force the past to speak a consistent language.